Show that the Brillouin function approaches the Langevin function as j goes to infinity. What are the limits of the Brillouin function as j goes to 1.5 and alpha goes to 0? So we recall the Langevin function. Its L as a function of alpha is cotangent hyperbolic alpha minus 1 over alpha. And the Brillouin function is dependent on the total angular momentum quantum number j. As a function of alpha, it's 2j plus 1 over 2j, cotangent hyperbolic 2j plus 1 over 2j alpha, minus 1 over 2j, cotangent hyperbolic alpha over 2j. So first we're going to look at the limit as j, the total angular momentum quantum number, goes to infinity. So this is basically the classical limit. So we have an infinite quantum number. So if you analyze what happens to the ratio 2j plus 1 over 2j as j goes to infinity, it's basically 2j plus 1 divided by 2j. Now, what will happen is 2j will become much greater than 1, so the top will turn into the limit as j goes to infinity, 2j divided by 2j. So the top and bottom are approaching infinity at the same rate, so this limit is 1. And also, we can look at cotangent hyperbolic alpha. Now, cotangent hyperbolic alpha is cosine hyperbolic alpha divided by sine hyperbolic alpha. And cosine hyperbolic alpha is e to the alpha plus e to the minus alpha over 2. So e to the alpha plus e to the minus alpha. Sine hyperbolic alpha is e to the alpha minus e to the minus alpha over 2. So these 2's will cancel. So we're left with this ratio. So we have cosine hyperbolic alpha equals e to the alpha plus e to the minus alpha divided by 2. And we have sine hyperbolic alpha equals e to the alpha minus e to the minus alpha over 2. And we should also note that the derivative of cosine hyperbolic alpha with respect to alpha is so e to the alpha will become e to the alpha, e to the minus alpha will give us minus e to the minus alpha. So this turns into sine hyperbolic alpha. And the derivative of sine hyperbolic alpha with respect to alpha, on the other hand, is e to the alpha plus e to the minus alpha over 2. So this turns into cosine hyperbolic alpha. We're going to utilize this in the Taylor series expansion. So if we do a Taylor series around alpha is equal to 0. So Taylor series around alpha is equal to 0. So we're working on cosine hyperbolic alpha to start with. Alpha is in the vicinity of 0. So this will be approximately, first we have to evaluate the function at alpha is equal to 0. Alpha is equal to 0 gives us 1 plus 1 divided by 2. So this is going to give us 1. So that's the first term. Then we take the derivative with respect to alpha. We're going to obtain sine hyperbolic alpha. Evaluated that at alpha is equal to 0. We will have e to the 0 minus e to the 0 over 2. So that is going to give us 0. So this will give sine hyperbolic 0 multiplied with alpha minus 0. And then the second derivative, Sine hyperbolic derivative, remember, is cosine hyperbolic. So it's cosine hyperbolic 0 divided by 2 factorial alpha minus 0 square. The third derivative gives us sine hyperbolic evaluated at 0 divided by 3 factorial alpha minus 0 cube. And the fourth term is cosine hyperbolic 0 divided by 4 factorial alpha minus 0 to the fourth power, and we have higher order terms. So this can be summarized as 1. This term is 0 because sine hyperbolic 0 is 0, and this one is also 0. So we have a non-zero term here, 1 over 2 alpha squared. So it's 1 plus alpha squared over 2. And then we have another non-zero term here, that is 1 over 4 factorial alpha to the fourth power. So this is alpha to the fourth power divided by 4 factorial. What is 4 factorial? 4 times 3, 12 times 2, 24. And we have higher order terms. Now if we do the same exercise for sine hyperbolic alpha, sine hyperbolic alpha evaluated in the vicinity of alpha is equal to 0 is, first of all, sine hyperbolic 0, which is 0. Then we have the derivative cosine hyperbolic 0, alpha minus 0. The derivative gives us sine hyperbolic, so sine hyperbolic 0 divided by 2 factorial alpha squared, and then another derivative cosine hyperbolic 0 divided by 3 factorial alpha minus 0 cube, and higher order terms. So this gives us 2 non-zero terms here. Cosine hyperbolic 0 is 1, so we have first term alpha. The second one here, this is going to give us 0, but this one will give us alpha cube over 6, and then we have higher order terms. Now how about the ratio cosine hyperbolic alpha divided by sine hyperbolic alpha in the vicinity of alpha is equal to 0? So this is the behavior we will find. It is 1 plus alpha squared over 2. So we're expanding cosine hyperbolic, and alpha to the fourth power over 24 plus higher order terms. This will be divided by sine hyperbolic alpha expansion alpha plus alpha cube over 6 plus higher order terms. Now you can see that the first term here will be, in order to obtain 1, you have to multiply alpha with 1 over alpha. So if you multiply this with 1 over alpha, you will obtain 1, and 1 over alpha times alpha cube over 6 will be alpha squared over 6. And then we subtract this. We obtain alpha squared over 2 minus alpha squared over 6. That is 3 alpha squared over 6 minus alpha squared over 6, 2 alpha squared over 6. That is alpha squared over 3. And then we have plus alpha to the fourth power over 24, higher order terms. Now, in order to obtain alpha squared over 3, I have to multiply this by alpha over 3. So we have alpha over 3. This gives us alpha squared over 3, and alpha to the fourth power over 3 times 6, 18. And then we have to subtract this, etc. So this goes on like that. So we basically find that the first two non-zero terms in the expansion of cotangent hyperbolic alpha in the vicinity of alpha is equal to 0 consists of 1 over alpha and alpha over 3. And then we have higher order terms. Okay. Now, so we can apply these two results to the expansion of the Brillouin function as j goes to infinity. So we note that Brillouin function as j goes to infinity, function of alpha, will be, so I have found that 2j plus 1 over 2j becomes 1. So this becomes 1, this becomes 1. So this is cotangent hyperbolic alpha. So that's the first term, cotangent hyperbolic alpha, minus 1 over 2j cotangent hyperbolic alpha divided by 2j. Now, as j goes to infinity, you can see that alpha over 2j term is going to 0. So therefore, it's equivalent to saying alpha is going to 0. So because alpha over 2j is going to 0, j is going to infinity. So in that case, I know exactly what happens. This is cotangent hyperbolic alpha minus 1 over 2j. Now, remember, I have found that if you have a cotangent hyperbolic of something where something goes to 0, it is 1 over that variable plus variable over 3. So the variable is now alpha over 2j. So 1 over alpha over 2j becomes 2j over alpha. And then I have plus alpha over 3. So plus alpha over 6j. So these are the first two non-zero terms. So this becomes cotangent hyperbolic alpha minus 1 over 2j times 2j over alpha becomes 1 over alpha. And 1 over 2j times alpha over 6j becomes minus alpha over 12j squared. Now j is going to infinity. This term is going to 0 because j goes to infinity. And therefore, the function that I have obtained here is basically cotangent hyperbolic alpha minus 1 over alpha. So this proves that in the classical limit, indeed, I find the quantum mechanical result, Brillouin function, with the total angular momentum index j as a function of alpha approaches the Langevin function, classical result, L of alpha, as j goes to infinity. So this is basically the end result. Now the second part of the question was asking what happens when j is equal to 1 over 2. Okay, so j is equal to 1 over 2 implies 2j plus 1 over 2j will become 2 times 1 over 2 is 1, 1 plus 1 is 2, 2 divided by 1 is 2. And the 2j term will become 1. So what I will obtain here is Brillouin function for j equals 1/2 as a function of alpha is 2 cotangent hyperbolic 2 alpha minus cotangent hyperbolic alpha. So I have substituted for 2j plus 1 over 2j2, 2 cotangent hyperbolic 2 alpha minus 1 over 2j becomes 1 minus cotangent hyperbolic alpha because 1 over 2j is 1. So this is basically, if I plug in the meaning of cotangent hyperbolic, this is e to the 2 alpha plus e to the minus 2 alpha divided by e to the 2 alpha minus e to the minus 2 alpha. And then I have minus cotangent hyperbolic alpha, which is e to the alpha plus e to the minus alpha divided by e to the alpha minus e to the minus alpha. So the Brillouin function at j is equal to 1/2 as a function of alpha is 2 e to the 2 alpha plus e to the minus 2 alpha. Now I concentrate on the denominator. I see that this is in the form a squared minus b squared, which is a minus b times a plus b. So this is e to the alpha plus e to the minus alpha multiplied with e to the alpha minus e to the minus alpha. And then I have minus the cotangent hyperbolic alpha term, e to the alpha plus e to the minus alpha divided by e to the alpha minus e to the minus alpha. Now I can write these two in this with this common denominator. So what I need to do is to multiply this term with e to the alpha plus e to the minus alpha, top and bottom. So I will obtain, writing these two terms with a common denominator, 2e to the 2 alpha plus 2e to the minus 2 alpha minus e to the alpha plus e to the minus alpha parentheses squared e to the alpha plus e to the minus alpha e to the alpha minus e to the minus alpha. Okay, so this is now, if I expand this square term, let's see what this means. So 2e to the 2 alpha plus 2e to the minus 2 alpha. I already had these two terms. Now e to the alpha squared becomes e to the 2 alpha with the minus sign. It is minus e to the 2 alpha. And then I have plus 2e to the alpha e to the minus alpha. That's 2. So with the minus sign it becomes minus 2. And then I have plus e to the minus alpha squared. That is e to the minus 2 alpha. With the minus sign, it's minus e to the minus 2 alpha divided by e to the alpha plus e to the minus alpha, e to the alpha minus e to the minus alpha. So you can see that I have a simplification here. 2e to the 2 alpha and e to the 2 alpha will make only 1 e to the 2 alpha. So e to the 2 alpha. And the same thing will happen for this e to the minus 2 alpha term. So plus e to the minus 2 alpha minus 2 divided by e to the alpha plus e to the minus alpha, e to the alpha minus e to the minus alpha. Now I realize that what I have on top is e to the alpha minus e to the minus alpha parentheses squared. So the top one is e to the alpha minus e to the minus alpha parentheses squared. Is that so? So we have e to the 2 alpha, e to the minus 2 alpha, and minus 2, the cross term, minus 2 times e to the alpha, e to the minus alpha, which is 1. And in the denominator, remember, I have e to the alpha plus e to the minus alpha multiplied with e to the alpha minus e to the minus alpha. So this term will disappear with the top term. So I'm going to be left with e to the alpha minus, so the Brillouin function for j is equal to 1/2 of alpha will be the sine hyperbolic alpha, e to the alpha, e to the minus alpha over 2 divided by cosine hyperbolic alpha, e to the alpha plus e to the minus alpha over 2. So sine divided by cosine gives us tangent. So this is tangent hyperbolic alpha. And the third question was, what if alpha is equal to 0? So alpha is equal to 0. In that case, we have the limit alpha goes to 0, bj of alpha. This is 2j plus 1 over 2j. Now this term is approaching 0, so that means I'm working with the limit of cotangent hyperbolic alpha as alpha approaches 0. So first I obtain 1 over alpha, so that means 2j over 2j plus 1 alpha. So that's the first term. So I have two j over 2j plus 1 alpha. And the second term here is alpha over 3, which corresponds to 2j plus 1 alpha over 6j. So that's the second term. 2j plus 1 alpha over 6j. And then I have minus 1 over 2j, cotangent hyperbolic alpha over 2j. Again, this is small, so it's going to be first 1 over this term, 2j over alpha. So I'm using the same Taylor expansion, 2j over alpha. And then I have plus alpha over 3 in the cotangent hyperbolic expansion, remember. So this corresponds to alpha over 6j. Alpha over 6j. Okay, so first I see 2j plus 1 over 2j and 2j over 2j plus 1 will cancel, so I will be left with alpha to the power minus 1. So that is the multiplication of these two. Now multiplication of these two will give me the square of 2j plus 1 and 12j square in the denominator. 12j square, and then I have an alpha here. This term, 1 over 2j times 2j over alpha, is minus alpha to minus 1. And then this term, 1 over 2j times alpha over 6j, with the minus sign becomes alpha over 12j squared. Now you can see that alpha to the power minus 1 will cancel, and I will be left with, so let's open up this square, 4j squared plus 4j plus 1, and then I have a minus alpha here, so it's going to be minus 1 in alpha parentheses divided by 12j squared, and this gives me plus 1 and minus 1 cancel, 4 divided by 12 becomes 1 over 3, so I have j plus 1 of the j's will disappear as well, divided by 3j. So you can see that this 4 will make this 12 3, and j square, the square will get rid of one of the j's here, becomes j plus 1, and I have a leftover alpha here. So my conclusion is that the Brillouin function of j as alpha goes to 0 becomes j plus 1 over 3j alpha. So that's the limit I'm looking for. All right. So in this problem, we looked at the limit of the Brillouin function in the classical case where j goes to infinity. You have an infinite quantum number. And then we looked at what happens as j goes to 1/2 and alpha goes to 0. And we recall the Langevin function, the classical function, cotangent hyperbolic alpha minus 1 over alpha, and Brillouin function, 2j plus 1 over 2j, cotangent hyperbolic 2j plus 1 over 2j, alpha minus 1 over 2j, cotangent hyperbolic alpha over 2j. So we do this in a few steps. In the limit j goes to infinity, this term becomes 1. 2j plus 1 over 2j becomes 1, as we have shown. And cotangent hyperbolic term will become basically cotangent hyperbolic alpha. So the first term becomes cotangent hyperbolic alpha. The second term is minus 1 over 2j cotangent hyperbolic alpha over 2j, j goes to infinity, cotangent hyperbolic of something really small. So in order to figure out how cotangent hyperbolic function behaves in the vicinity of 0, I have written cosine hyperbolic and sine hyperbolic expansions Taylor series around alpha equals 0. The cosine hyperbolic gives me this, sine hyperbolic gives me this. If I divide these two, I obtain cotangent hyperbolic expansion around alpha equals 0. So that's 1 over alpha plus alpha over 3. So in this case, this would correspond to 2j over alpha plus alpha over 6j, because that's alpha here is replaced by alpha over 2j. So that's what I have done here. And basically, I see that I obtain Langevin function as j goes to infinity. If I substitute j equals 1/2, so this ratio 2j plus 1 over 2j becomes 2 and 2j becomes 1. So it's basically 2 cotangent hyperbolic 2 alpha minus cotangent hyperbolic alpha. After going through some algebra, I realized that this is tangent hyperbolic alpha. And what happens as alpha goes to 0? In the case alpha is equal to 0, both of these terms are small. So I look at cotangent hyperbolic expansion where the variable is 2j plus 1 over 2j alpha, and the second case, the variable is alpha over 2j. I use the same result here, and I obtain my final answer after some algebra, j plus 1 over 3j times alpha.